Hello, everybody. We're going to start our discussion here for our first lab topic, which is called minerals. Obviously, one of the most fundamental things that we have here on Earth and that Earth has to offer us. And they're a pretty fascinating bunch of substances that we're going to kind of take a look at. But we're going to sort of build up to what minerals are and how to identify them eventually. And to start that conversation out, we kind of need to talk about some of those basic characteristics of minerals. And obviously, what is a mineral? Um, this is a naturally occurring inorganic substance having a definite chemical composition. Yes, you can read, but I want to really emphasize each one of those kind of ideas being naturally occurring. They're here. They've always been here or have formed over the Earth's history. Inorganic means they are not alive, nor were they ever alive. And a definite chemical composition means that they have a specific, well, as we'll learn, arrangement of atoms. And so we'll talk about what that causes them to actually look like. And there's the definition for inorganic. Um, and so how do we make a mineral? Basically, we take some elements and we put them together, sometimes one or sometimes more than one. And elements, if you are kind of having horrifying flashbacks of maybe high school chemistry, you've taken some in college, yeah, they kind of come up here. But we're not really going into a huge amount of detail on them. But those elements are basically atoms that we can make from the periodic table. So atoms are the smallest and simplest units of matter. Um, we're going to look at the periodic table in just a second, but an atom is what you've always thought of as an atom. Hopefully, you have some vague recollection of the structure here. You've got a little ball of particles in the middle. Those are your protons and neutrons. And then the ones that are whirling around at the outside of that nucleus are the electrons. And so the protons are the ones with positive charge, neutrons have no charge, and electrons have negative charge. And that has huge implications for how substances come together to form compounds and how minerals are basically structured. So important stuff. Now, here's the deal. The periodic table is where we see all these elements, and I'm going to kind of break it down for you here. So if you look over at, let's go all the way to the top right, number 2, that is helium. So here's the deal. If you have one atom of helium, you still have helium. It's an element, but you only have one single atom of it. Now, typically, if you were to think about a balloon with helium, the kind that float, that has billions and billions of atoms of helium in it. And so you typically, when you find elements in nature, they're made up of many, 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 many atoms of whatever that element is. So a more like reasonable example would be like a piece of aluminum foil. So if you look at number 13 on there, aluminum foil is a metal. And if we only had one atom of aluminum, we would never, ever, ever even see or understand that it's even there. So when you think about even a piece of aluminum foil, which is extremely thin, you have, again, billions and billions of aluminum atoms all linked together to create that. Technically, it's actually a very thick sheet of atoms, but in that, when they all come together, have very specific properties like shininess and foldability and things like that. So that's kind of the chemistry background of our elements. You are free to click in the slideshow if you have it open, the little link at the bottom there. It's a song about the elements. I'm going to spare you right now from playing that. It's really fun if you want to learn the words. You'll see if you click it. But for now, I just wanted to kind of put together the structure of how things come together to make what we know of as minerals. So it starts as a single atom, which is an element, but if you put a lot of those elements or atoms together, you get a bigger piece of that element, such as the aluminum foil example. Okay, so if we look at all of the ones that are on the periodic table in terms of elements, by percentage, if you look at the Earth, there aren't really a lot of most of them. So in other words, what there is a lot of on Earth are a select few elements. So look there at the top of our list, we have oxygen coming in at 46, almost 46.5% of the Earth's crust by mass. And then surprisingly, the second place winner of the most common element on Earth is silicon. And you'll find that to be true in a lot of the elements, I'm sorry, the minerals that we look at throughout this little investigation. So see it coming in over around 28%. And then we kind of move on down. You start to see some of the metals coming up, like aluminum, iron, calcium, sodium, magnesium, and so on. Just a quick kind of, I don't know if you can see my cursor, but hopefully you can. If you look at the hydrosphere, which is that column there, about the third one over, it says hydrosphere. And if you look at what's in it, it has 33% oxygen, 66% hydrogen, and 1% other. Well, think about that. Hydro or hydrosphere, that's your water on Earth, so H2O. And look at that, H2, meaning 66% of it is hydrogen. And then O, the remaining chunk of it, is oxygen. So kind of an interesting little thing there that basically says that the hydrosphere is made up of H2O, and that's water. Over here, the troposphere is the atmosphere of the Earth that we live in, so the lowest portion of the atmosphere. And if you look at that, that is actually really wild because we rely so much on oxygen, and oxygen is a very common element here on Earth, but most of the oxygen is actually locked up within the Earth's crust, so within rocks and minerals. And some of it is airborne, and that's the 21% that we actually breathe in. And that 21%, that's all we've got. So when we take a breath, most of that breath, only 21% of it on average is actually oxygen. So that's a really weird thing to think about, considering how important it is for us to actually survive on. The majority of the air that you breathe in is actually nitrogen. So 78%, that is like, it's just an inert kind of harmless gas, doesn't do anything to you. It's somewhat useful within your body, but predominantly we really siphon out the oxygen using our lungs and things like that. So the other there would be things like water vapor and carbon dioxide and methane and various trace gases that are within the atmosphere. So for minerals, getting kind of back to the focus here, some minerals are special because they're composed of only one element. And I want you to take a look at these examples. So on the left, you have a yellow crystalline looking substance, looks kind of chunky, and you may recognize it. You may almost in your mind be able to smell it. That is sulfur, and sulfur is made up of just one element. It is all atoms of the element S. And so if you go back to the periodic table, you can see an element called S, and that's what it looks like when you have a whole bunch of them, like billions and billions of them all locked together. And the other one on the right, not a lot of us have too much of this lying around, but you can probably guess that is actually gold. And again, it's an element, but it's also considered a mineral because we tend to associate minerals with things that have some sort of value to society. So gold is both an element made up of billions and billions of atoms of gold, but it's also considered a mineral as well. And the symbol for gold, if you're wondering, on that periodic table is AU. Again, it's kind of one of those weird things that from history, we had AG and AU. The one with the G in it is not gold. Ironically, it's actually silver, whereas AU is the symbol for gold. Now, typically, that's kind of a rarity. Most of the elements, or I'm sorry, the minerals that we are going to see and work with and actually look at lots of pictures of are made up of multiple elements, so combinations of different elements from the periodic table. For example, the left one, which actually kind of looks a lot like gold, is not gold. It is called pyrite. It looks a lot like gold, and if you look at the little chemical combination there, it's iron and 2 atoms of sulfur. Believe it or not, that yellow one we just looked at is actually a linked part of this mineral called pyrite, and it has to basically combine iron and sulfur together to get the pyrite that you see there. And for those of you who don't know, that's where we get the term fool's gold from. People were finding this stuff back in the old days when they were all excited about going west and exploring new territory, and they would find this stuff lying around, like, oh, we found a whole bunch of gold, and then they'd bring it in to kind of turn it in for actual dollars or some sort of trade, and the people would look at them and say, this is garbage, this is not gold at all. And it isn't. It is useful. We can actually melt it down and extract the iron from it, which is a valuable metal in its own right. But by itself, pyrite is not really useful. It's actually just kind of pretty. On the right, you have another one called quartz. And if you look at this is a cool mineral because it has uses, but it's got a lot of interesting properties. The crystal shape being one of them that you see there. When it forms, it actually creates a crystalline pattern based on the way the atoms within it are joined together. So what you're seeing actually is silicon and oxygen bonded together to create what's weirdly enough a clear crystalline substance. So we in chemistry would call quartz silicon dioxide. So if you're a chemistry fan, that's another little trivia for you to talk about at dinner tonight. So quartz, very common, has a lot of great properties, which we'll talk about, and is actually composed of the top two elements within the Earth, oxygen and silicon consecutively. So kind of an interesting one there. Some other little factoids and things that you should know. All minerals are rocks. So when I pick up a mineral from the earth, whether it's a big piece or a little tiny piece, it's still a rock. I mean, it's a hard substance. You know, it could break a window if you threw it hard enough, that kind of thing. So, however, one of the weird things is not all rocks are actually considered minerals. So the example on the lower left there is actually, I'm sorry, I skipped, we need to mention at least galena for now. Galena is a mineral, but it's also a rock. I mean, look at it. It looks like you could just grab it and throw it, so that's a rock. But down on the lower left, we have a sample of coal. And coal is a neat one because it is kind of feels like a rock. It's a chunk of material that you could grab and throw around, but it's not considered a mineral. And I guess the question here as you're thinking through this is why not? And the answer is because it's actually made up of dead plants or animal remains. So it's actually a kind of a sludgy tar that hardened into a rock, but it is not a mineral because it's made up of once living things, which means it's organic. And that means it is absolutely not a mineral for that reason. It's still useful, but it's not a mineral, officially by definition. Glass is actually the same thing. If you think about, you probably have found chunks of glass at the beach sometimes that are all polished and worn down. It's easier to hold and less dangerous. It behaves just like a rock. It's a chunk of stuff that you can pick up and throw around, but it is not a mineral. And that's because, well, even though it contains minerals, we made it. It's a man-made or human-made substance that is not naturally occurring. Key point. So that just kind of goes back to the trivia of what is a mineral really. All right. Now this part I'm going to kind of glaze over really fast. Only one thing I'm going to say that you need to know from all this is minerals are all crystalline. So when I, pick up a mineral and look at it, and sometimes visibly I can see that it is a crystal. It has a very specific shape or a pattern that you see. However, it is not always as obvious unless you kind of look at it with a microscope. Some of them don't look like they're crystalline, but they all are. And the reason for that is the way the atoms come together, the different elements that are a part of it, all those atoms kind of come together in a certain way or a pattern or an arrangement, and that is what makes things crystalline. So here's the deal. Bold-faced words have a specific internal arrangement of atoms, and that comes up over and over. That specific internal arrangement of atoms is why every mineral is unique for every different way that it is unique. So if it has a funny color or smell, or if it has a certain crystal pattern, shape, whatever, that's all from the specific internal arrangements of atoms. And here's where I get really fast. You can arrange them in chain sheets or just have them randomly isolated, and that creates various minerals that have specific looking kind of appearances. The silicates are really what do that, and those are the ones with silicon and oxygen in them. Again, that's a lot of chemistry and a lot of stuff that you really don't need to know for the purposes of this course, certainly the lab. But I just wanted you to see that that's why you're going to see some of the patterns that you see when you look at minerals. And here's an example such as quartz. Carbonates are interesting. We're going to actually do this little demonstration for you when we get to it. When there is calcium and oxygen in the same mineral, you can actually disrupt the bond that's holding them together with some, basically like an acid, like hydrochloric acid, or even some strong fruit juice. And that will cause your mineral or your sample to start bubbling and fizzing. And what happens is it's busting up the carbon and the oxygen and creating carbon dioxide gas. So it's kind of a cool little process. And we have a specific one called calcite that will do that. And I will show you that when we get to that part of the lab. So here's where we stop and take a little break. The next big chunk of minerals is, all right, so that's what they are. Well, how do you classify them? And so key point here is we go forward. I am not going to post specific videos within eCampus on this. You're going to find the links that are embedded within each slide. So what you'll be able to do here is you'll be able to click through the slides on your own, and you will see at some point video links that are posted in there. And I just wanted you to know that that's how we're going to do this, because while you're reading through the slides, you can click the little video link, and then I'll pop up and talk about and show you some of those properties and how we actually go about classifying the minerals. And I will say once more, since we're on this slide right now, as we go forward, minerals are classified based on their physical and chemical properties. So physical properties, things you can see, feel, observe, that kind of thing. Chemical properties are a little more mysterious, like what's going on beneath the surface. You know, if you had a crystal shape, you can obviously assume there's a lot going on there. That's a chemical property. And of course, all minerals, how we classify them, how we determine these physical and chemical properties, that is all based on whatever the internal arrangement of atoms is. So I just felt the need to say that again. But again, so as we go through further into this, as we classify minerals, the videos that explain all this stuff will be embedded within this slideshow. So just keep that in mind and kind of go through it on your own. But occasionally, most of the time, you'll see a little video within each slide or every other couple of slides. All right, so we will see you soon.